Okay, following on from my previous video on the Year 12 January internal assessment for the pure paper, I'm now just going to do the applied paper. So this was 30 minutes, so it shouldn't take me too long to go through it for you guys. Again, please come and find me if you are still stuck and have questions, but hopefully this will answer many of the questions you have. Okay, question number 1. An ornithologist is studying Humboldt penguins in South America. She records the masses of the first 5 Humboldt penguins that she catches. State the sampling method that she has used. Okay, so the sampling method is opportunity sampling. Because it just so happens that that penguin was in that place at that time. So it's opportunity sampling by definition. You need to know your 5 sampling techniques for this course. Part B, give one advantage and one disadvantage of the ornithologist using the sampling method to record penguin masses for her study. So there are a number of answers you could have here. My advantage is it's a quick method. It's quick to do because you're just catching 5 penguins and recording their masses, and then you can move on. A disadvantage is it's not representative of the population. Because, for example, you may have one gender of penguin staying with the nest or the eggs while the other one hunts, for example. So either saying it's biased or not representative. Question number 2. Matthew is investigating the daily mean temperature T in the UK. He takes a sample of the first 15 days in September 2015 for Heathrow from the large data set. The results are shown below. State with a reason whether T is a discrete or a continuous variable. Okay, so it is a continuous variable because temperature can take any value. It is not limited to just integers, for example. It can take any value, and we can see that here. We've got some decimals going on. It is a continuous. Okay, given that the sum of T is 223.9 and the sum of T squared is 3,384.21, find the mean and standard deviation of the temperatures. So good, we don't have to calculate those, it's all calculated for us, which is great. So actually this data up here is pretty much irrelevant. So the mean, which you might denote as T bar, so the mean of the temperature, and that's just going to be the sum of T divided by N. So the sum of T divided by N, well, we've got the sum of T is 223.9, and we know that N is 15, okay, we're told there's 15 days chosen, and that comes out to be 14.9 degrees Celsius, 1 mark for that. The standard deviation, which you might denote as sigma, or sigma subscript T. We can use the formula from the formula book. So it is the sum of T squared over N minus the mean squared. Now just be careful, we don't want to use the rounded mean that you've just evaluated. You want to use the full calculated display, or even better, just plug in 223.9 over 15 again into there. Otherwise you'll get a rounding error. And it comes out to be 1.67589, blah, blah, blah. And we need at least 3 sig fig. So I'm looking for either 1.68 perhaps, or 1.676 or something like that. Okay. And part C, suggest one way that Matthew could make better use of the large data set for his study. Well, just consider what he's actually trying to study. He's trying to study the daily mean temperature in the UK, yet he takes samples only from September, only from Heathrow, and only in the year 2015. So any one of the reasons, use more months, use the other year group from the data set, or use one of the other 4 locations is a valid answer for that. Question 3. The histogram in figure 16 shows the age distribution of people living in inner London in 2001. Use the histogram to estimate the number of people aged under the age of 25. Okay, so this is between 20 and 30, so we're looking at 25, so essentially just half of this bar. And we've got frequency density up on the left-hand side there already. So that looks to be 33, and there's 20 of them. So 33 times 20 for that one. And then for this, we're looking for, let's put 58 times 10 over 2. So 58 times 10 over 2 for this bar here. Add them together, and that'll give you that the estimate is approximately 950. Part B, use the table to calculate an estimate of the mean age of these people. Okay, so we've got a table here. So now moving away from the histogram onto the table, it's going to represent the same data. But we don't need the histogram anymore. We're now looking to estimate the median. So we've got 2,770. So therefore we're looking for the 1,385.5th person. Okay, where does that person lie? Well, it's going to be somewhere between 30 and 40. Okay, so we're looking in that range. So what you need to do now is you need to linearly interpolate this to find an approximation for the median. So what I do to linearly interpolate these kind of questions is I just draw a little line between the knowledge bits that I know, what I'm trying to find, and then what my answer will be. So for example here, the 1,240th piece of data, the age is going to be 30. The 1,810th piece of data, the age is going to be 40. I am looking for the 1,385.5th piece of data, and that is my median that I am looking for. Now this is a linear line. This is where linear interpolation, that phrase, comes in. So therefore I just want to say, well, the gradient between this point and this point is the same as the gradient between this point and this point. That's where the formula comes in. If you're happy learning the formula, then that's fine. 1,810 minus 1,240, the difference between those two values, divided by the difference in those two values, equals the difference in those two values, 1385.5 minus 1240, divided by the difference in those two values, which is x minus 30. And if you come to solve that, you'll get that x is equal to 32.5526, blah, blah, blah. So 32.6 to 3 sig fig. Again, when in doubt, 3 sig fig is a good accuracy to leave an answer to. Okay. All right, that finishes the stats. On to mechanics. A point particle starts at A and uniformly accelerates from rest to v meters per second in 40 seconds. It then maintains the velocity for a further 40 seconds before uniformly decelerating for 20 seconds to rest at B. Sketch a velocity time graph for the motion of this particle. So, velocity time graph. So there's my time, there's my velocity. All right, it starts at A and uniformly accelerates from rest to V. So that means when t is 0, it starts at 0. So it's starting at rest. So it starts at t is 0, v is 0, and it's going to accelerate uniformly. That means a straight line in 40 seconds. So straight line to v meters per second in 40 seconds. Great. That's the first part of it. It then maintains this velocity for a further 40 seconds. Okay, so maintaining the velocity means it's going to be a horizontal line. It maintains it for a further 40 seconds, so therefore we're now at 80. And then it uniformly decelerates for 20 seconds to rest at B. So it's going to come down to here, another 20 seconds, takes it up to 100, and it's now at rest again at the point B. Okay, so that's my velocity time graph, and that will give me 3 marks. Happy days. Part B. Given that the displacement from A to B is 1,400 meters, calculate the value of V. Okay, we cannot use SUVAT on this problem because the acceleration has changed. Okay, it's positive acceleration here, 0 acceleration here, and negative acceleration here. So though acceleration is constant in each of these 3 parts, it's not constant across the whole system. So we cannot use SUVAT. We are instead going to use the fact that the area under a velocity time graph is the displacement. So the area of this trapezium is going to be the sum of the two parallel sides. So 100 across the base and 40 across the top. Divided by 2 times the perpendicular distance, and the perpendicular distance is the height, which is our unknown v. So that is the area under the graph, and we know that's 1400 because we're told that the displacement is 1400 meters, and everything's in meters and seconds, so I don't need to do any kind of changing of that. This is a nice linear equation in v, which tells me that v is 20 meters per second. That's the answer to that. And then part C, nice easy little one marker. Calculate the value of the acceleration in the first 40 seconds of the motion. Again, you need to know this. The acceleration of a velocity time graph is the gradient. So the gradient of this line here is the difference in the vertical, which is 20, divided by the difference in the horizontal, which is 40. So it's 20 over 40, or 0.5, and that'll be a meters seconds to the -2. Yeah, answer to that one. Question number 5. At time t equals 0, a small ball is projected vertically upwards with a speed of u meters per second from a point A that is 20 meters above the horizontal ground. The speed of the ball at the instant immediately before it hits the ground for the first time is 21 meters per second. The ball hits the ground for the first time when t equals t seconds. The motion of the ball from the instant it is projected until the instant just before it hits the ground for the first time is modelled as that of a particle moving freely under gravity. Using this model, show that u equals 7. Okay, so this is a Suvat problem. Okay, it's moving freely under gravity, and we must take g to be 9.8. So I'm just going to draw a little sketch. I think drawing a little sketch of these problems is always beneficial. So it's being projected vertically upwards. So it's being launched upwards with a speed of u. I don't know what u is. I'm told to show that u is 7, but just like in one of the pure paper questions, you can't use that fact to show that fact. You must arrive at that fact. And then it hits the ground with a speed of 21, and it is accelerating downwards with an acceleration of 9.8, and I know that this distance here is 20 meters. So I've got a nice little diagram now to help visualize exactly what is going on. So I'm now going to draw up my Suvat table. So S, U, V, A, and T. It's projected vertically from a point A, so I'm going to call this point A. It doesn't say the point when it lands, so I'm just going to call it point X. Doesn't really matter what you call it. I'm just going to put in my Suvat table AX, just to illustrate that I'm going from the point A to the point X. Displacement, well, I'm going to take up to be positive. Okay, you can take down to be positive if you want to, which is fine. You just need to be consistent. So I'm going to take up to be positive. So from A to X, it's gone down by 20 meters, so therefore the displacement is minus 20. U is upwards, so that is positive. V is travelling downwards at that point at 21, so therefore that's minus 21. And the acceleration is down, so therefore that's minus 9.8. And T, well, from A to X, we're told that it's T seconds, so capital T. So for part A of the question, I need to show that U is 7. So I want a Suvat equation which doesn't contain T. So V squared equals U squared plus 2AS is the way to go. So V squared equals U squared plus 2AS. So that's 441 equals U squared, which is unknown at this stage, plus 2AS. So that's going to be plus 2 times minus 9.8 times minus 20. That tells me that U squared is 49. Therefore, U is 7 as required. Okay. If you took down to be positive, you've got to do a little bit more work just to illustrate that U is indeed 7, because actually your U from your value here would be minus 7, because you're taking down to be positive. This is why up is positive is better in this situation, because then your U is already in your right direction. Part B, find the value of T. So again, the Suvat table still stands, but I just want to find the value of T. You can use any Suvat equation here. I'd recommend perhaps one that doesn't contain a U, but in this case, it doesn't actually matter because you're even told that U is 7. So you're given all 4 of those. So it doesn't matter what Suvat equation you used. I'm going to say V equals U plus AT, just because that's probably the simplest one. So that's minus 21 is equal to U, which is positive 7, plus A, which is minus 9.8 times T. Okay, that's my unknown. And if I solve that, I'll get that T is 20/7, which is the exact answer. But in mechanics, exact isn't necessarily better. Rounding to 3 sig fig is good. So 2.86 seconds. That's my answer. Again, hopefully you found this useful. If you are unsure of anything, then again, please just ask or watch the video again. But hopefully that's answered most of your questions, if not all. And we can move forward with the next part of the course. Thank you.